Hi, everyone. Welcome to today's session on secure multi-party computation. So we have three talks today. And for the first talk, we have Maxime with us, who will be speaking on Foleage, F4 OLE-based MPC for Boolean circuits. Over to you, Maxime.
All right. Yeah, thank you for the introduction. So this talk is about computing Boolean circuits in the preprocessing model. And so for those of you who are not really familiar with this setting, the idea is that many MPC protocol can actually benefit from the parties knowing some random coins, which are correlated in some useful way. So speed up the protocol and achieve a better communication also. So basically, modern MPC protocol would be split into two phases. First, in an offline phase, the parties would generate and would be given this correlated randomness, which would then be used in the online phase with the actual input to achieve an online phase which is both information theoretically secure on the one hand, and also super efficient communication-wise and computational-wise. This is well known. It started basically with the work of Beaver in '91 and has known a lot of progress in the recent years. So basically, the main question here in this setting is how can we make this preprocessing real efficient in terms of, especially in terms of communication? Well, the traditional way of generating random behavior triples is to use random mobile use transfers, and especially OT extension protocol, where basically two parties will generate this a constant small number of random obvious transfers, which would then be expanded using only cheap symmetric crypto. So yeah, it's super efficient in the two-party setting. However, if you want to generalize it to the n party, basically, you need to do that for each pair of parts. So it scales quite poorly in this setting. We have a quadratic growth in the communication. So that's yeah. For multi-party, it's not that efficient. Well, and yeah, in order to improve on this matter, roughly 10 years ago, initiated by the seminal work of the Speeds protocol, have been using some homomorphic encryption in order to go down to something which is linear in the number of bytes. And the concrete implementation, which is this overdrive, which is basically the state of the art in this setting, achieve some very good efficiency because it is able to produce hundreds of thousands of multiplication triples per second. However, there is a huge caveat in the sense that these protocols are only available over large fields. So in order to, if you want to compute some Boolean functions, it's still not really efficient. More recently, a new paradigm has been introduced by Boyle et al. That they called silent preprocessing, where basically two parties would enter some minimal interaction and to derive some short correlated seeds, which is seed A and seed B here, which would then be locally expanded without further communication into low correlated sequence of those correlations. And so even though you need to do that for all pairs of parties, so you still have this growth in n square, the first interaction, this minimal protocol to derive the seeds is solo in terms of communication, that it's still very useful for large circuits and like a decent number of parties. And it works on par with the overdrive in terms of efficiency. Nevertheless, there is still a caveat here is that, well, in order to be able to achieve n party, you need to have some property called programmability, which is basically in this construction only possible over large. So we are still stuck with this set. But this protocol can also be used over small fields if you only restrict to the two-party setting. And it enables to achieve a very good efficiency because it can generate millions of triples per second with the state-of-the-art recent implementation such as soft-spoken or expand covolent. So this construction are known as silent OT extensions. All right. So the landscape of correlation generators is basically the following. Over large field, you have two settings. Either you consider homomorphic encryption, and you can scale linearly in terms of the number of parties, but also linearly in the number in the amount of correlation you want. Or you can scale logarithmically in the amount of correlation, the randomness, and but quadratically in terms of users. But it's in terms of efficiency, it's still okay. On the other hand of the spectrum, over small fields, you have a very good efficiency in terms of communication and very good efficiency in terms of concrete computation, but it's restricted to two parts. The things changed a little bit a couple of years ago, where for some quarters and I, we introduced a new PCG, which enabled to generate beaver triples for any finite fields up to q equal to 3. So we basically almost bridged this gap, but there is still this the question of the Boolean field is still open, and as far as we know, the best way of generating n-party correlations for F2 is still quadratic in the number of parties and linear in the number of correlation. And the question is, can we do better? And can we do better with also a very good practical efficiency? So in this work, we achieved that. Basically, we introduced a new protocol to generate beaver triples over F2 based on a first generation over F4, and then locally, transforming it to the correlation over the binary field, which for the two-party setting enables a very small amount of communication, so logarithmic in the number of randomness, and with a very, very good concrete efficiency in terms of computation, because you are able to generate tens of millions of triples per second, and also has a very small seeds. And in the multi-party setting, we cannot quite be as good as what we get with the programmable PCGs, but the amount of first communication is still okay, because it just only requires a broadcast of a single bit per party per triple, which makes it okay. Asymptotically, it's worse than overdrive, for instance. But given the constants in our implementation and the constants of using FHE over large field, basically, we estimate that our protocol would be more efficient than overdrive for amount of parties of several hundreds. All right. So here are some numbers that are given by our implementation, where on the top rows you have the performance for n parties, for 10 parties, sorry, and on the second half you have the generation for 2 parties, and both are used to generate 1 billion of beaver triples over F2. So basically, you see that for our implementation is very fast, and the red part is because well, the main bottleneck here are the local computation and not the communication anymore. All right. So okay, let's go into the construction. Before that, let's recall the framework for generating pseudo-random correlation generators for a correlation known as oblivious linear evaluation, or OLE. So it's easier to explain in this setting, and it's not hard to see that basically 2 OLEs are equivalent to 1 beaver triple. So well, what you need to know is that an OLE is just this correlation. So you have 2 factors, U and V. So one party would get 1 factor U, the other one would get factor V, and they both get random additive sharing of the product U times V. And the idea of this framework is that, okay, we want to generate those OLE correlation over some finite field FQ. And the observation is that if we knew how to generate only a single OLE over a big ring R, which is isomorphic to a product of FQ, then all the parties could locally apply this isomorphism in order to get all these correlations over FQ. So in the first constructions, the Boyle et al. They would use some polynomial ring, FQ John X mod F, where F is a polynomial which splits completely in infinitely FQ, and they would set the factors U and V of the form A times E plus F, where E and F are sparse polynomials, such that the product is now a linear combination of sparse-ish polynomials, which can be easily distributed using function secret sharing of sums of point function. So this was basically the main idea with all this class of PCGs, and but it's the fact that it was restricted to large field is because you need this polynomial to split completely in FQ. So last year in this paper, we suggested to use a more general algebraic structure known as group algebra, which is basically a linear combination a formal linear combination of elements in the finite group G, and with the coefficients are in some finite field FQ. You can think of it as multivariate polynomial rings, basically, because under suitable presentation, they are completely isomorphic, and you can think of it as really as multivariate polynomial rings. So the construction would work very similarly, and the security assumption is now some decoding problem on those group algebras that we call group quasi-abelian in-order decoding assumption. So translating it over F4, which is exactly the main focus on this work, we can set G to be a direct sum of Z mod 3Z, such that my group algebra is now this multivariate polynomial ring, and the rest of the framework applies basically similarly. What's extremely interesting here in this paper is that actually group algebras are the right structure when you want to do fast Fourier transform algorithm, and we give very fast implementation of FFT in this group algebra, so that the evaluation of the OLE, which is basically applying this FFT, is actually extremely fast here in this. All right. Okay, so now that we can construct very efficiently a PCG for Beaver triple over F4, remember that the main question was how can we use that? I mean, can we generate Beaver triple over F2? Because of course we can still use Beaver triple over F4, embed F2 into F4, but if you do that, you increase the cost of the communication in the online phase, which this is not exactly what you really want to do. So you really want Beaver triple over F2. But the observation here is that given the fact that, so you can write F4 as, it's a degree 2 extension of F2. So if I write theta to be some element of this basis, I can decompose all my Beaver triple in this basis. And the observation is that from that, you can actually generate one Beaver triple over F2. So each party will reveal one bit, their share of B1 here, and they would be able to compute this A0, A1, and C0 plus B1, A1, which is actually a valid Beaver triple over F2. So wrapping up, the protocol is now the following. You generate your oblivious linear evaluation over F4. Then you transform that into Beaver triple over F4. So 2 OLEs equals 1 Beaver. You broadcast one single bit for each F4 triple, and then you can use only local computation to generate your M Beaver triple over F2. And that's it. And the only communication is really this broadcast in the middle and the minimal expansion, the minimal seed generation in the beginning. Okay, so that's it for this. It turns out that so this is for n parties. You do that for all pairs of. So each party will just reveal their share of V1, as I said. But it turns out that in the two-party setting, you can do even better than that, because there is a very small trick. But you can see that contrary to remember that I said that you need two OLEs over F4, let's say, to generate one Beaver triple over F4. But in fact, again, using the fact that F4 is a degree 2 extension, and it really works because it's a degree 2 extension. It wouldn't work for a larger extension. With only one OLEs over F4, you are able to generate one Beaver triple over F2. And this is now completely silent. I mean, each party can do that locally without further communication. However, it doesn't extend to more than two parties. But that's how we are able to achieve a very good conflict efficiency in the two-party setting. Yeah. All right. That's for the basic construction, but of course, if we want to make it as practical as we would want, we also needed to apply some good optimization in every part of the protocol. So the first part is basically the seed generation, so this minimal interaction protocol, which uses so I mean, as a black box manner, some distributed point function. I don't really want to go into that detail, but the main idea is that each party will share some, I mean, we'll have some GDM-like tree whose leaves represent a random additive sharing of 0 for all elements of which are 0, basically. And there is only one leaf which is not 0, because so this is for sharing one unit vector. And remember that you wanted to share a sparse vector. So a t-sparse vector is nothing but like a sum of unit vectors. So you do that t times, and you are able to share t-sparse vectors. So this is for the basic idea, but the main thing about the distributed part is a protocol by Dorner and Gelat that showed how if the parties have an additive sharing of the path presenting this non-zero value, then they can generate this in a distributed manner quite efficiently. But here, the observation that we make is that tailored in the fact that we are really using this group algebra, and we really work with the group Z mod 3Z to the power of t, then basically a product e times e prime here will always, I mean, all the monomials will always the form x to pi times x to pj, which is exactly x to pi plus pj, which means that the parties natively hold ternary shares of the noisy positions, which was not true earlier. And so there's one thing the parties could locally, I mean, they could transform them to a binary additive sharing of the position. But we would want to make use of the fact that they natively hold this ternary share. So the idea to make use of this observation is to adapt this DPF construction by using not binary tree anymore, but ternary tree. It seems simple at first glance, but in fact, it turns out that well, the proofs are not that simple, and you need to. I mean, there are a lot of technical things that you need to make it work. And there are some pros and cons when you want to adapt this distributive set of protocol into this ternary set. On the good side is that since the tree is now flatter, the expansion becomes 20% faster, and the number of runs is also reduced by some logarithmic factor. On the other hand, we need to use more. I mean, sorry, I didn't really talk about it, but in order to keep the consistency on each level, you need to add some correction words. And in the two parties, I mean, with binary trees, you could use only one correction word per level. Here, you need 3. So the size of the seed is larger, and so the amount of communication is bigger. And also, the distributed protocol makes use of 1 out of 3 OT instead of 1 out of 2, which also makes things a little bit less fast, let's say, but still very practical. So that's for the seed generation, but we can also benefit from actual other optimization that were already known for DPF, for binary DPF, basically. So the first one is to use regular noise, which enables to reduce the domain of the evaluation domain of the DPF, and this increases a lot. I mean, decreases a lot the communication that we need to use. And some technique known as early termination, which enables us to gain an additional 64 times speed up by just keeping to the fact that we only work over F4, which is a very small domain, and we don't need all those 128 bits size diff. Okay, that's basically all what I wanted to say. As a wrapping up, what you can remember from this talk is that Foleage is a very efficient protocol, which is we estimate it to be actually the faster one for computing Boolean circuits up to several hundreds of parties. And to do that, yeah, we introduced several layers of the optimization and different part of this work. And yeah, if there are some cryptanalysts in the room that want to talk about the security of this QAZ assumption, I'm really glad to talk about it later. Thank you.
Yeah, thank you, Maxime, for the wonderful talk. We have, I guess we don't have time, but I guess I will allow a very quick question from the audience. Okay, so I do have a question, but I'll ask you offline.
Okay.
Yeah. The second talk of the session is on actively secure polynomial evaluation from shared polynomial encodings. And we have Sebastian with us to talk about their paper. Over to you, Sebastian.
Yeah, thank you. Can you hear me well? So I talk about actively secure polynomial evaluation from shared polynomial encodings. This is a work from the University of Stuttgart, from the Institute of Information Security. And of course, it's in the MPC session. So this is because we want to evaluate polynomials in multi-party computation. So let's talk about the MPC setting first. So we are on the same page. Of course, you know that in multi-party computation, we have secret inputs. And then we have a function which we want to compute on the secret data. And then we have outputs which might be public or might be secret depending on the use case. And in particular, I'm always assuming an actively malicious dishonest majority. So we might have up to n-1 malicious parties, which means in this three-party example that one or even two parties might deviate arbitrarily from the protocol. And for this setting, in order to compute arithmetic functions, the state-of-the-art protocol is speeds and its improvements, such as overdrive. And in this protocol, additions and multiplications with public values is non-interactive, so we can just perform these operations locally on our secret shares. But when we want to multiply secret values with each other, then we need interaction between the parties. So we need to exchange some messages, and we also need pre-processed data, classically in the form of beaver triples, which we already heard. But in this setting, typically the beaver triples are over a much larger domain, and they are also authenticated using a secret MAC key. And the classical approach would be that we have only addition and multiplication gates in our circuit. And then for every layer of multiplications, we require one communication round and, of course, sufficiently many beaver triples, which we computed ahead of time in the offline phase. And this communication round complexity can be a problem, especially if the latency is high, then these communication rounds can present a bottleneck. And this is where our work comes in, because with our approach, we replace beaver triples by a new form of structured randomness in order to reduce the communication down to one amortized rounds. And we will see shortly what this amortized means here. So the idea of somehow optimizing structured randomness is nothing entirely new. It has been already introduced in recent years, for instance, to optimize typical operations and privacy-preserving machine learning, where you might have so-called matrix triples in order to optimize matrix multiplications, or convolution triples to optimize tensor convolutions. But so far, this has nothing to do with the round complexity, because these operations, matrix multiplication or tensor convolutions, they have a multiplicative depth and therefore a round complexity of 1 anyway. But another typical operation is polynomial evaluation. And there, depending on the degree of the polynomial, we have a larger depth. And unfortunately, for multivariate polynomials, previously no one-round solutions existed, or at least those which existed come with exponential size of the structured randomness. And this is then, of course, inefficient for large polynomial degrees. And we address this problem by introducing a new form of structured randomness, which we call polytuples, in order to evaluate multivariate polynomials, and also can be applied to comparison operations in one amortized round. How does this work? For this, I have to talk about a concept called randomized encodings. So this will now seem a bit formal, but I think we can get over this, and we need this in order to understand what polytuples are. So randomized encodings is an idea, is a concept that exists for more than 20 years already, but it was not explicitly used in the speeds like MPC context yet. So the definition is, here we have some sets, and we have a function f from x to y. We have, and this is later the function which we want to securely compute. And instead of computing f directly, like this, we take some additional randomness. So we have our input space x, and we take some additional space a where we sample randomness. And then we compute a so-called randomized encoding. And this output now somehow encodes our actual function output. And then we want that there exists a reconstruction algorithm to go from here to the actual function output. And we also want privacy, where in this case, privacy means that the output of our randomized encoding doesn't leak anything except for what can be deduced from the function output anyway. Okay, so how does this make sense? I mean, if we just say f hat equals f, then this works. So f would be a randomized encoding of itself. That obviously doesn't really make sense. So the idea is that we use a randomized encoding that is somehow easier to compute in a multi-party computation context than computing the function f directly. So let me give an example, namely for the simple multiplication of two values. So we have f of x0 and x1 equals the product of those. And classically, you would do this using Beaver multiplication, which requires a Beaver triple. And this is actually exactly the same, just written as a randomized encoding. So our randomized encoding of f now consists of 3 components. The first component is just x0 minus a0, where a0 is some random value from the just one component of this randomness space. So this is just a masked input value. Then the second component is also the other masked input value. And the idea is then that the reconstruction algorithm will later multiply these two masked input values. And the third component of our randomized encoding is just a correction term, which accounts for the fact that we didn't actually multiply our inputs, but we multiplied our masked inputs. So we need to add this reconstruction, this correction term in the reconstruction in order to actually obtain the product of these two values. And In general, our randomized encodings, which we use in MPC, will always have this form. When we have m input variables, so here m equals 2 because we have 2 input variables, then the first m components of our randomized encoding are just the masked input values. And then the remaining components, so in this case, there's only one remaining component. The remaining components of the randomized encoding is something that's easy to compute if we assume that these masked input values are already public. Okay? So here, more generally, we have function f that depends on m input variables, and we want to compute a randomized encoding f hat on shares of inputs and randomness. So this randomness has been shared in the offline phase. So what do the parties do? First, they exchange all shares of the masked input values. And this is done parallelly. And each party then reconstructs these masked input values locally. And then afterwards, the parties can locally compute shares of the remaining components of the randomized encoding. So going back to our example, they can now compute shares of this value y2. And then they can also reveal these shares, and then locally reconstruct also y2, and then plug that into the reconstruction algorithm of the randomized encoding in order to compute the function output. And a slightly modified version of this protocol can also be used if we want to, in the end, have shares of the output instead of the actual output. So if we don't want to make the output of our function public, it can also be done using a slight modification. Of course, all of this only works if these, what I call remaining components of our randomized encoding, so these components which we compute after the first round, can be computed from these masked input values and the shares of the inputs and the shares of the randomness which the parties have from the offline phase. So these randomized encodings can also be concatenated and composed. So let's go one layer higher, where we say, okay, we have 4 input variables and we want to compute the product of those. So that means this is a monomial of degree 4, a multivariate monomial. And by using the same Beaver technique, we can already get down to degree 2. So now this is a product of 2 polynomials of degree 2 with some correction term. And then we can recursively apply randomized encoding technique again in order, so let's look at this degree 2 polynomial, for instance. So we recursively apply this randomized encoding technique in order to go down to degree 1. Okay, so that means we get 4 polynomials of degree 1 in the X for all of these degree 2 terms, and there were 4 of these degree 2 terms. So in total, we get 4 times 4, which is 16 degree 1 terms in order to compute this monomial. Or more generally, if our degree here is any power of 2, then we get oops, where is it? Here. Then we get 4 to the power of n terms here on the leaf layer, which is, if we plug in that m equals 2 to the n, then that's O of m squared. So this is a result that has been known for a relatively long time, but it has never been applied to multi-party computation. And it is also known that like the degree here on the leaf layer, this can be, if we count not only the x, but also these random factors, these randomness factors into the degree, then we have a degree of at most 3, and this is the theoretical minimum can be achieved. So what does our work now do? Our work, our randomized encodings, improves this m squared and also applies the whole thing to multi-party computation. So first, how do we improve on the m squared? So here I have the same picture as in the last slide, where we decomposed this, we encoded this y0 using 4-degree-1 polynomials. And of course, this is also done for the y1 and for these two binomials contained in the correction term. So here, for instance, for this term, we likewise have 4-degree-1 polynomials. And here you can see that in both of these two randomized encodings on the left side and on the right side, there's twice the same polynomial, x0 minus a0. And if these polynomials can be used in different reconstructions, then we only need to output them once. And this reduces the output size. Though there is a problem, namely, when we compose these two randomized encodings, and we concatenate them with the randomized encoding on the layer above, then we cannot simply say that we use the same randomness here and here. In general, this would no longer be a secure randomized encoding. So that's a problem in general, but for this special construction, we were able to prove that we can indeed do this. So we can here reuse the same randomness, and this is still randomized encoding. So by identifying which polynomials we can use in the reconstruction of multiple polynomials on a layer above, we need to, we just reduced the output size of the resulting randomized encoding. And this means that the output size reduces from m squared to m times log m. Then we also extended this approach to generic monomials of this form, where we can also have degrees larger than 1. This is relatively straightforward. And we extended it further to arbitrary polynomials. And even further, we extended the approach to other tree structures. So we don't always need to decompose it into 2 factors, but it can also be 3 or more factors. And for all of these generalizations, we present a recursive formula to compute the exact output size and randomness size for all resulting randomized encodings. So of course, we also did comparisons and benchmarks. So here, of course, what are we even benchmarking? In the MPC offline phase, we would compute the structured randomness that is required for these randomized encodings as an authenticated tuple. And this tuple, like all of these random masks and random products of these random values and so on that are required in the randomized encoding, they together as an authenticated tuple, we call this a polytuple. And the offline phase to compute this can be based on different existing techniques that can also be used for computing beaver triples. And the offline phase is linear in the tuple size. And then in the online phase, the number of elements communicated over the network equals the output size of the randomized encoding. In the online phase, our protocol needs 1 round to exchange all these masked input values, and then 1 opening round. So this was the second round in my MPC example. So the question is, why do we call this amortized 1-round protocol? That is because our protocol can be used in a multi-round fashion, where we compute multiple functions in sequence. So we compute the polynomial fn and then use the output of that to as an input for the next polynomial and so on. And here, the second round of the one protocol can already be used as the first round of the next protocol using a minor optimization. So that means for every additional polynomial which we want to evaluate, we only get one additional round, and that's why we say this is an amortized one-round protocol. Here we have the theoretical comparison with other approaches for computing, for evaluating a degree D binomial. So there are m variables, and all of them are to the power of d divided by m. So that means the total degree is always d. And classically with beaver triples, you would need to do this as a tree of multiplications, which means you get a round complexity of log d, and bandwidth and tuple size linear in M. Then there was this first one-round approach, which had the problem that the tuple size is exponential. So here, for instance, if d and m is the same, then we get 2 to the power of m minus 1 components of this, what we call binomial tuple. This is, of course, a problem in practice. And the bandwidth is, or the communication number of elements which need to be communicated in the online phase is m. And our polytuple approach slightly increases this to O of m log m, but then the tuple size is only m log squared of m. So much, much, much better than the previous exponential size. Here again, the round count does not include the opening round, which is needed for all of the compared protocols. And this table includes only one example of a polytuple. As I said, there might be you could use different tree structures and so on. Depending on the setup, we can get different trade-offs. For example, we can use more communication rounds by splitting up our polynomial into, like, first evaluate part of it, then use that as an input to the next polynomial. And it's possible to trade rounds for tuple size and communication. So by using more rounds, already with 2 rounds, the tuple size in total and the communication requirement is greatly reduced. And we can also use different variants of our randomized encoding, as I said, tree structures, to trade reduced bandwidth against larger tuple size while keeping the same round complexity. This means that our protocols can be adapted to different setups, such as bandwidth rate restrictions, network delay, or local computational power. Yeah, we have implemented our protocols as an extension of MP speeds, which is the state-of-art implementation of the speeds MPC protocol. And our implementation has been submitted and accepted as an Asiacrypt artifact and will be published with the paper. And based on that implementation, we benchmarked, for instance, the evaluation of a Gaussian function with, with 32 variables with different network delays. So here we have 2 milliseconds, 5 milliseconds, or 10 milliseconds network delay. And in all cases, in blue, you see the default MP speeds implementation, and in orange, you see our implementation, which is a factor of 1.5 to 2 times faster. We can also employ polytuples to compare values by doing just a bitwise comparison on the bit representation of the values, and this can then be used to sort items. And for sorting 40 items, we see that, like, depending on the algorithm, we have 2 different figures here, and you can see that our protocol outperforms the default MP speeds implementation, and also in the dotted green line is MP speeds with ADA bits enabled, which is like an optimization for bitwise operations, which sometimes is an optimization, sometimes actually is not an optimization, but our protocol outperforms both of them. And we can also use the same approach, of course, to compute comparisons in a machine learning context. So that might be useful, for instance, for an argmax layer. So here we have we had a toy machine learning network, and when benchmarking only the argmax layer, we get an improvement of like a factor 1.5. And then this is also still an improvement when benchmarking the whole machine learning network, even though only this one layer has been improved. So to wrap this up, we introduce a new family of randomized encodings for the evaluation of multivariate polynomials and new correlated randomness for that, which we call polytuples. Our randomized encodings have the smallest known output size for arbitrary monomials, and we integrate this into MP speeds, and our approach evaluates multivariate polynomials in just one round of online communication, amortized, and our tuple size is significantly lower than for existing single-round approaches, and also multi-round computations still yield improvements. We evaluated the performance, as I just said, and this shows that polytuples speed up the computations compared to fewer multiplication. So thank you for your attention, and yeah, I give it back to the session chair.
Yeah, thank you, Sebastian, for the talk. So while the next talk will be in the online mode, so while that is set up, we can quickly take a question. Any question from the audience?
Hi there. Thank you very much for the wonderful talk. So I just wanted to quickly ask, I believe you are aware of Polymath, the paper called Polymath from PETS 2022.
I don't know that one.
Okay, so they also use some type of preprocessing for, basically the idea is that if you have a multivariate polynomial, you can always preprocess all possible monomials that will appear when you compute a difference. And then that allows you also to multiply to do this whole polynomial evaluation in one round. But the issue is exponential preprocessing.
Mm-hmm.
So in your paper, you're getting polynomial preprocessing. So basically, you're saying that you can evaluate in one round with information theoretic security, pretty much, if you generate these tuples and whatever.
Yeah, assuming you implemented your offline phase information theoretically, yes.
Yeah. So in one round, for circuits that admit a polynomial representation of constant of polynomial degree.
Yeah.
Have you compared to the results on constant round MPC, perhaps?
Yeah, so we didn't compare to any like other constant round MPC paradigms like Gabel circuits also or something like that. But referring to that paper, you said from 2022, but it sounds a bit like the other 2018 paper from Cho et al., which I cited, where they presented this one round approach with exponential tuple size. And then our contribution is, of course, to get rid of this exponential tuple size.
Yeah, but just on the constant round aspect, what I'm saying is there are like information theoretic constant round MPC protocols for certain specific families of circuits, and maybe it's worth exploring if you enable a wider family, perhaps.
Yeah, that might be possible.
Okay, so let's thank Sebastian once more. Okay, so the last talk of this session is on the dishonest majority multi-party computation over matrix rings. And Hong Qing will present the paper to us. Is he connected already? Okay, just bear with us until we connect with the speaker. Hong Kong, can you hear us? Are you online?
Can you hear me? Hello?
Hello. Yeah, we can hear you.
I'm sorry. I'm sorry. There's something wrong with my network. Okay. Hello, everyone. I'm Hongqing Liu from Shanghai Jiao Tong University. Today, I am honored to introduce our new work, Dishonest Majority Multiparty Computation over Matrix Rings. This is a joint work with Chao Pingxin, Chen Yuan, and Taoxu Zhou. Multiparty computation (MPC) allows several distrustful parties to compute a public function without leaking their private information. According to the number of corrupted parties, we classify MPC into honest majority and dishonest majority protocols. Here we focus on malicious adversary, where the corrupted parties can arbitrarily deviate the protocol. In the beginning, MPC protocols are restricted to large fields. Recently, a series of MPC protocols have been designed for binary fields and integer rings Z2K. We can even construct an MPC protocol over non-commutative rings in the honest majority setting. Naturally, we want to ask a question: can we design an efficient MPC protocol for some non-commutative rings in the dishonest majority setting against a malicious adversary? In this work, we answer this question affirmatively. We design an MPC protocol for matrix rings which contain m times m matrices over a finite field F. So why do we choose matrix rings? On the one hand, the matrix plays an important role in privacy protection machine learning. The leading lies of machine learning, such as fully connected and convolution layers, involve numerous matrix operations. On the other hand, many applicable non-commutative rings can be represented as a matrix. For example, quaternion rings can describe rotations in 3 dimensions space. Thus, they are applied in computer graphics and area space. We observe that any element of a quaternion ring can be written as a 4 times 4 matrix. Let's start with the classical speed protocol, which is an efficient dishonest majority MPC protocol. To tolerate n-1 parties corrupted by a malicious adversary, speed protocol applies an authenticated secret sharing scheme. The core idea is to append a message authenticated code, MAC, for addictive sharing. We can detect the addictive errors introduced by the adversary with the help of MAC. Assume there are n parties P1 to Pn in the initialization step. Each party Pi obtains the global key, the key shell alpha I of the global key alpha. Then for each addictive sharing of X, all parties need to generate the addictive sharing of alpha X as the corresponding MAC. Obviously, we can locally compute addition and scalar multiplication for authenticated secret sharing. To multiply two authenticated sharings, X and Y, we need to prepare an authenticated build triple A, B, C in the preprocessing phase, where A and B are uniformly sampled from the field, and C is the product of A and B. In the online phase, we only need to open two values, D equal to X minus A and E equal to Y minus B. These two openings leak no information about X and Y, since A and B act as random masks. Then we can locally compute the authenticated sharing of Z, product of X and Y. This protocol works for a single element of a field. Now we turn to the matrix ring over this field. Without modifying the global key, we only need to extend the secret and MAC to matrices. Compared to the traditional space protocol, this new protocol makes full use of the structure of matrices and avoids redundant communication. Similar to the original space protocol, this protocol also supports some local computation, including addition and multiplication with a public matrix on both left and right sides. This is because the global key can be regarded as a scalar matrix, which lies in the center of matrix rings. For the multiplication, we only need to extend authenticated build triples to matrices. In the final equality, note that the computation of DB and AE requires left and right linearity respectively. The previous two protocols use an element of field as the global key. We observe that if we replace the global key with a column vector, the MAC is comprised from a matrix to a vector. In this way, the size of authenticated secret sharing is reduced from 2m squared to m squared plus m, which is only half when m is large enough. However, this improvement brings a problem. The new secret sharing scheme can only locally compute addition and left multiplication with a public matrix. The right linearity does not hold anymore. This change affects our multiplication protocol. We cannot locally compute the term AE in the final equality without right linearity. So how to compute it? To solve this problem, we need to achieve right linearity for our authenticated secret sharing. Here, we resort to the transpose of matrices. In this case, we need to prepare a new type of correlated randomness double sharing, which is a pair of authenticated sharing of a random matrix and its transpose. For each multiplication gate, we prepare a multiplication sextuple A, AT, B, C, R, and RT, where A, B, and R are random matrices. C is the product of A and B. AT and RT are the transpose of A and R, respectively. A multiplication sextuple is a combination of a build triple and two double sharings. In the online phase, we first follow the original protocol to open two matrices D and E. Then we open F by using the transpose of A, R, and the public matrix E. This opening still leaks nothing due to the mask of RT. We realize the right linearity with the cost of an extra opening and the consumption of two double sharings. Note that this new multiplication protocol requires an additional round, which can be eliminated by using function-dependent preprocessing. In the function-dependent preprocessing phase, all parties know the circuit but have no idea of the input. They can make use of the knowledge of circuit structure to reduce the communication round and complexity in the online phase. From now on, we will focus on preprocessing phase. The main task is to prepare a multiplication sextuple for each multiplication gate. First of all, let's consider how to generate an authenticated secret sharing. We resort to a two-party primitive, vector oblivious linear evaluation (VOLE). In a VOLE instance, Alice inputs a vector U of length m, and Bob inputs a scalar x. Then Alice and Bob receive two vectors of length m, v and w, respectively. The sum of v and w is the product between vector u and scalar x. We can obtain n-party VOLE with n-squared invocations of two-party VOLE between each pair of parties. Since the global key remains unchanged during the whole protocol, we can apply VOLE to generate the max shells by setting the input of Bob as the king shell. Now we proceed to random VOLE, RVOLE. The pseudo-random correlation generator (PCG) technique is used to reduce the communication cost. Here we introduce a function, expand, that generates a random vector U with the input of a seed S, which can be regarded as a PRG. Compared to VOLE, Alice only needs to input a seed instead of a whole vector U. The communication cost of RVOLE is only sublinear in the vector length m. In contrast, the communication cost of VOLE scarcely linearly in the vector length m. It is not easy to clarify the detailed construction of RVOLE in such a short time, therefore I will omit this part. We only need to know that RVOLE needs to invoke two fundamental primitives, base VOLE and OT. Here, OT refers to oblivious transfer. We will discuss two variants of RVOLE, subfield VOLE and our VOPE, which optimize OT and base VOLE respectively. This is the first variant of RVOLE, subfield VOLE. In the classical subfield VOLE, the vector chosen by Alice is defined over a subfield. Here, we take an equivalent view to fit our setting. In a subfield VOLE instance, Alice still inputs a seed S that can be expanded to a random vector U of length m1, like RVOLE. The difference is that Bob inputs a vector of length m2 instead of a scalar. The subfield VOLE returns two m1 times m2 matrices, V and W, to Alice and Bob respectively. The sum of V and W is the owner product between two vectors U and X. Here is the definition of the outer product between two vectors. We can regard a subfield VOLE instance as M2 instances of RVOLE with the same seed and the different scalars. These scalars form the input vector chosen by Bob. Subfield VOLE can reduce the seed to reduce the number of OT instances. Based on subfield VOLE, we propose vector oblivious product evaluation, VOPE for short. VOPE is used to obtain the additive sharing of the owner product between two random vectors. We observe that when M2 is also large, we can introduce a new expand function to generate a random vector of length M2. In this case, both Alice and Bob only need to input a seed. So, what is the benefit of replacing the input of Bob from a vector to a seed? Recall that all variants of RVOLE have to invoke base VOLE as a building block. Compared to subfield VOLE, our VOPE protocol transforms these base VOLE instances into random VOLE instances. This modification allows us to make use of the advantage of PCG technique again, which reduces the communication and computation complexity further. Finally, we show how to compute matrix multiplication C between two random matrices A and B, which correspond to a pivot triple. This is the bottleneck of our preprocessing phase. Previously, most work were based on homomorphic encryption. These works encrypt each row of matrix A and each column of matrix B, respectively, then the matrix multiplication is decomposed into several inner products. In our work, we take a different view of matrix multiplication. We regard matrix multiplication as the sum of the outer products between vectors. For each outer product, we can apply our VOP protocol. Alice and Bob randomly choose M2 seeds from the seed spaces respectively. Then Alice uses each seed to generate a column of matrix A, and Bob applies each seed to obtain a row of matrix B. In each VOPE instance, Alice and Bob only need to input the corresponding seed. Previous works rely on the inner product of vectors, while our protocol resorts to the outer product of vectors. Our protocol provides a new method to compute random matrix multiplication. Well, let's consider the performance. This is a theoretical analysis of the online phase. Compared to traditional speech protocol, both our protocol and speech plus matrix reduce the communication complexity of each multiplication gate from OM cube to OM square. The advantage of our protocol is the shell size and the computation cost, which reduces around 15% shell size and 40% of number of multiplications compared to speech plus matrix when M is large enough. We also implement the online phase of all three protocols. The experimental result shows that our protocol achieves 1.38 to 1.85 times speed up compared to speed plus matrix, which roughly matches our theoretical analysis. In the pre-processing phase, we first analyze the communication cost of random VOLE, subfield VOLE, and our VOPE. We also display the communication cost of homomorphic encryption. From random VOLE, subfield VOLE to our VOPE, we observe that the communication cost is decreased step by step. The communication complexity of our VOPE is even comparable to homomorphic encryption. We calculate the number of base VOLE and OT instances and benchmark to estimate the runtime of VOLE-based protocols. Note that homomorphic encryption also argues the efficiency with a benchmark. In the aspect of the experimental result, our VOP protocol achieves a 1.44 to 24.17 times speed up compared to homomorphic encryption. This speed up is prominent when matrix size M is large. Although VOLE-based protocols are believed to be applicable in random matrix multiplication, we are the first to analyze the concrete efficiency, and our VOPE makes a large improvement compared to random VOLE and subfield VOLE. At the end of the speech, we make a brief summary of this talk. In the online phase, we apply a new authenticated secret sharing by replacing the global key at MAC with vectors. To deal with the non-commutative property of matrix rings, we apply the transpose of matrices to design a multiplication sextuple as correlated randomness for each multiplication gate. Previous work, CKR plus 21, only requires 1 over M communication cost compared to traditional speech protocol, while our protocol optimizes the shell size and computation complexity. In the pre-processing phase, almost all previous works for secure matrix multiplication are based on homomorphic encryption. Here we list CKR plus 21 as a representative work against a malicious adversary. We follow the technical line of VOLE and design a new protocol VOP specialized for matrix multiplication. Our work has shown the potential of VOLE-based protocols in matrix multiplication, and we hope our work can attract the interest of VOLE in matrix multiplication and more applications. Here we list the main reference of our slide. Thank you for your attention. If you have any questions, please feel free to contact me at my email.